Thank you everyone for coming. And today, based in Vancouver, Canada, Ray is a full-stack developer with proficiency in many web frameworks. This particular talk focuses on an intersection of fields that I'm really fond of: microcontrollers, Gleam, and hobby projects. Ray has been doing the hard job of figuring out how to make Gleam work under AtomVM, an effort to take all the fun properties of the bin, but in a tiny form factor. So let's start and give a warm welcome to Ray de los Santos.
Thank you so much. So thank you. And basically, as mentioned, my name is Ray de los Santos, and the talk is Microcontrollers with Gleam. So let's talk a little bit about me. That's not the best idea to talk about, but yeah, my name is Ray de los Santos. I live in Vancouver. Sorry for the accent. I'm from Spanish. My native language is Spanish, so sorry for that if you are missing something that I'm pronouncing not that correctly. But yeah, I live with my family here, so I should be around. My experience is more in the web-related space. So everything related to React, TypeScript, all the same frameworks that we use. I have around a decade working with all these frameworks and everything related to web. So that's my main domain of knowledge. But also I would like to talk about why this talk. So basically around 6 months ago, I started to learn about the Gleam language and everything related to the ecosystem, what was working, and I started my journey with the Lustre framework. Lustre framework is a very powerful framework for the web space. Also, it's full stack, and it has some new features like server components. But basically, with that experience and understanding the Gleam, I fell in love with the language, and it was like a good fit for me. And I wanted also to understand more about the Vim platform ecosystem and all the language around. So basically, at that time, also wanted to play around with microcontrollers for some hobby projects. I asked myself, why not try to Gleam? And that's the idea of this talk, to go about this journey, any tools that I was able to figure out, and I'm able to share as part of an open source project that we're going to be talking about. So first step, basically for my specific case, I wanted very low cost microcontrollers. And specifically, I wanted to implement something with ESP32, a platform. It's a very development board that is very cheap, relatively cheap, with some networking tools and all that. So when I was researching, I was understanding a little bit about the NERPS project, a very interesting one, but it was not applying by my case, at least not yet. I don't know if it's going to be improving a later day. I'm not that up to date with the NERPS project, but I figured out with AtomVM, I was trying to find out, this sounds like a good fit for what I'm trying to do. And I'm gonna go to giving an overview of what AtomVM it is. It's a Bean virtual machine, but it's more focused on controlling the RAM needed for running the microcontroller more than the performance of the VM. It's very performant, so it's more like it's trying to have some trade-off, but not a lot. And the main advantage that it has for what I was trying to figure out is more like the networking tools and the multiple peripherals that it has. I have been researching a little bit on the networking tools. Still not a lot that I can share, but for the peripherals, I'm going to give an overview in this talk. Basically in GPIO and I2C specifically. There's more peripherals in the AtomVM toolset, but for now, we're going to be focused on these two. And I'm going to go to the next question. What about the tooling for AtomVM? There's two main projects. The contributors of the main project, I believe, works on the two of them or multiple of them. But basically, it's the Ribar3 plugin that allows you to use Ribar3 and connect any Erlang base, like runtime. It's very easy to work with this plugin and implement like the flashing of the microcontroller. Also, there's the EX AtomVM that is like a Miss task recipe that allows you to use Elixir inside this AtomVM. There are some constraints. I believe not all functions are there is a subset of the Beam standard, And I believe not everything is working right now, but probably at some point in time, this may change in the long run. So basically, this is going to be a very code-centric presentation. I hope that it's not too dense, and I'm going to try to give like the general overview of what we are trying to achieve, not necessarily the details. The details I'm going to go by them, but that's not the important part. What I want to share is more like the general idea. And for now, we are going to talk about the blinky. Blinky is the hello world of microcontrollers. And I believe this video can explain better what it works. It's just to make sure that the internal LED is on and off by a period of time. And now we're going to go to the code on some of the idea of the setup that we need to do. INSI is the framework that I have been working on. It's an open source framework, and the repos are over there. And there's a framework that has some actors. It's an actors base for concurrency, handling the microcontroller peripherals. That's the idea of the project. And there's some INSI tools that the idea here is to try what it's already working in Rivar3 and Elixir, is giving the same tools, but for the Gleam space. And basically, Gleam normally has like a TOML file for setting up the variables, the dependency and the depth dependencies. But for this specific case, I added this like a special space for the INSI framework, and you can set up the platform and the port. These values that you can see in the screen are my default values that I do with an ESP32 platform with a port connected to an USB-C normal in a Mac OS environment. This change depending on your setup, but it's a good starting point, I believe. The imports needed. There's multiple imports that you may need to work on this. A lot of them are concentrated in the INSI platform. I'm gonna give later. I'm gonna explain a little bit more of these imports, but there's a group of imports from INSI, and also we are gonna use some of the Gleam libraries. Not all the Gleam libraries works out of the box with the AtomVM platform. So it takes a little bit of time to figure out what works and not. And that's something that in the long run, we believe we may be able to improve from the AtomVM project point of view, and maybe also from the Gleam project point of view. After you import, I'm going to give an idea of how the framework works for this case of the Blinky Hello World system. And basically what we are going to have here is we have a model. The model is going to have this concept of the state that we want to use to follow up with every side effect that we want to do with the hardware. And in this case, normally we are only putting the LED and the level. Level in the concept of microcontrollers is more if something is high or low. And basically, in this case, for the blinky behavior, if you have a low level, it's going to be off. The LED is going to be off. If you have a high level, it's going to be on. Normally, in Gleam, a main function is the starting point of the program. But specifically for the AtomVM project and system and runtime, you need to set up a start function. And in here, we are doing something simpler. We are calling an internal function that is do start and process sleep forever. This is the function of the start. And what we are going to do here is setting up a default model, because as a reminder, we're going to try to follow up how the models change with an store actor. And based on this change, the peripherals are going to be interacting with that information. So this is what we are doing here. We are going to try to start the store with the default model with LED set to a level low. After that, we're going to go to the internal LED actor. Internal LED actor is another, as I previously explained, it's an actor-based project, the INSI framework. And for this case, it's another actor. And what we are doing here is setting up the initial state of the actor with the pin information. A pin is just a space in the development board in this case ESP32. And what we are doing is setting up the values. Level is going to be low. I explained it before. Pool is the concept of transistor behavior. So we are making sure that the pool is going to be up, so we can register the information correctly as low or high. This is very common when you're working with microcontroller hardware. The port, in this case, this is a very dummy function. Basically, for PICO and ESP32, it's always 2, the internal LED. So this is returning 2. The direction is what kind of hardware is going to be, how it's going to be applying. And for this case specifically, it's an output because we only want to control the LED. We don't want to receive information from it. There's this update function. The update function right now is an experimental feature. What it tried to do is like run every time that the the actor change, update internally. It will run this function with the level and for GPIO, the level and the original model. This, I'm not sure if this is experimental. I'm not sure if that's going to survive in later revisions, but for now it's over there. So now we'll go to the internal LED. What we are trying to do is blink the internal LED. And for that, we are receiving as arguments of this recursive function, the idea of the store actor and the GPIO actor for the LED. And what we are doing here is getting the store value. With that value, we are transmitting this to the GPIO actor. So each of them has different concerns. And what we are doing is writing the LED level, high or low, depending on the current state of the loop. And for these, we normally do the sleep because we want to notice the change, and that is not that fast. After that, we call a set function inside the store actor, and what we are trying to do is change, switching the value of the level from high to low, low to high. After that, we continue the recursive function, and that should be all in the coding part of the Blinky solution. How to run this and flashing after a proper setup of the AtomVM. Using the INCDEP tools, we only run this command and connect it to the USB-C to the ESP32 platform board, and it should submit the runtime, and it should restart and make sure that it's blinking as I showed in the video previously. I'm going to go to a more complex case, trying to be as fast as possible, but it's going to be a very similar. I'm going to give another view of the actors working a little bit with a little bit more complex case. Also, the repo is always in GitHub if you need to take a look. So basically what we are doing, we have more wires around, but we have a joystick. This joystick tries to keep track of the I/O. Right now I'm pushing to the left side. And what I'm communicating is with the LED actor and also with the display actor. And now we're going to take a look on the code that make this possible. It's the same idea, the same patterns. We're going to setting up the model, but right now, we previously in Blinky, we had the LED level, but now we are also want to keep track of all the level of the joystick, up, down, left, all the directions and the middle button, because they are available for that joystick hardware. And we set up the default model, the initial state that the machine is going to be starting to run. And we start the same, start the store actor, and set up that model. The only difference here is this function. What we are doing here is a list of pins that we want to set up, and we are translating. There's a function transformation that is the second. This is what in Gleam is called a struct. So the first item is the pin number of the I/O. 12, 14, 27. This is particularly for that setup I show in the video. And the model, the function transformation, what it's trying to do is keeping the state updated. And it's going to change the model that we defined previously to the particular state. Everything in here is concurrent. And that was the main goal of the framework. So that's why you will see this list, and it will call the setup input. The setup input does the same as the LED, but only for the input IOs. So I skipped that code because it was too dense for the presentation. But in general, what we are trying is to transform every time that we detect in the hardware that something is the level is on or off, we're going to translate that to the model. Now I'm going to talk about other actors. We already talked about the GPIO LED, so that's not anything new. But in here, what for this specific case, for handling other actors that can extract information from the model and transmit it like an output, we created two different recursive functions. One is the sync internal LED, very similar to the blinky behavior, but I'm going to explain a little bit what's different, and also the sync display. The sync display extract the model information and it's going to transmit it to the I2C display that we show in the video. I2C is a two-wire protocol that is used for connecting to that specific display. For syncing internal LED, very similar to the Blinky one. The only difference is that we are not updating this. We are not updating the model directly in here, because what we want to do is react to the input of the joystick. And with this, so if we want to react to that, we leave that concern to the other setup of the inputs behavior. So basically, what we do here is only transmit what is shown in the model.let, and we are going to call the peripheral with a side effect. After that, this is going to be a recursive function running in another process. And now I'm going to show the recursive function for the sync display case. It's the same pattern. We receive the store actor and also the display UI actor. This actor is a custom one that was needed for this hardware, specific hardware. I didn't want to get into the details of that one because we will not have time in the presentation for that. But basically in here, with that actor, what we are doing is taking the model, and what we are doing depending pattern matching with Gleam. And what we are asking is if we find any of the fields that belongs to the joystick, then what we are going to do is translate this to an image inside the display. This case is going to be the up, down, left, right, middle, and blank, depending on the case. Something that you may, just in case, I'm going to go back to the video so we take a look again. So we are controlling two actors. One is for rotating the LED every time that I click on the joystick. As you may see, it's constant on because I'm pressing constantly the joystick. And you will see that we see the left arrow, and now I'm pressing down. You may see that there's a big delay, the display, and the issue that I believe is here is not specifically the actor's timing. It's more like the current protocol implementation that I did with Erlang. I believe it's not mature, it's not very good. So the fix for that probably is using some kind of, there's an if for Erlang. So probably that's the best approach. Use a C-based specific NIF feature to fix that display case. And also AtomVM has a new, I believe in one, it has a bug fix that allows you to not need it to write one byte at a time, but you can write the entire binary. And the way that this display works is more like you need to write a full binary to control the bits in the screen. And this is one off. You control the window and the space. There's a lot of documentation on how those displays works. But basically, that's what I work directly in Erlang, and it's working. But as you may see, it's not reacting as we want. So that's gonna be a drawback. And I'm thinking of researching more on figuring out a better solution for that. That's always going to be the journey, like finding out what works, what doesn't work. And for now, I believe at least I'm leaving some kind of framework for a starting point for someone else that is interested on playing around with Gleam and how it works with microcontroller. I explained it before. It's always the same. It's called the Flash inside the InCDEP tools, and it's going to transmit the runtime, the compiled runtime to the AtomVM machine. And basically, that's all. A special thank you. First to my family, to the organizers of the conference, thank you for everything that you help on. To all contributors and maintainers of the AtomVM project, a nice project, a very interesting one that allows a lot of work related to microcontrollers in the VM space, and also to contributors and maintainers of the Gleam ecosystem. Great people. I always like that it's so easy to to get help and to figure out anything that you may be missing of the language and the ecosystem. And of course, for all of you that was able to tolerate too much code, but I hope it's not that dense and it can give an overview of the experience more than anything else. You can reach out in the Gleam community. I'm always, if you tag me, I can reply very fast, I hope, in the Discord channel. I'm always receiving notifications in the Gleam community. And also all the core team members in Gleam, they are amazing. So please reach out to anyone and I may be able to help related to microcontrollers if I know how to figure out something. Thank you so much.
And thank you so much, Ray, for this great presentation. I'm wondering, is there any questions from the audience? No questions. There's a question on swap card. So it's, what is missing in Gleam to make your life easier, Ray?
What is missing? So one issue, almost everyone, one issue that I get used to is that it's very verbose. The language is very verbose. So people are thinking on something that can automate, like code generation or something like that. And I believe that's something that was like hard for me. But coming from TypeScript and other NIM language that have a very complex compiler time system, so that's something that I don't know if it's in research. That's something to ask the Gleam team to see if there's something else. But what I really like of the language is the simplicity. And for now, my main issues was not really on Gleam, was figuring out everything related to the Gleam, because you need to work in FF5 with Erlang. So I need to understand the two languages at the same time, and I didn't have any experience with the Vim ecosystem. So it was a new experience. This was a nice one. So what I'm missing, maybe compile time issues and probably some simplifications of arguments handling. But in the end, I'm okay with the verbosity of the language, and I'm getting used to, so I'm okay with that.
Great. Thank you so much, Adolfo. That was a great question. I have another question. Given that AtomVM is probably now compiling to WebAssembly, I was wondering if this work that you are doing, Ray, is maybe limited only for embedded devices, or maybe could be extended to like other platforms or territories?
I think so, but I don't know. I don't know a lot of the was M space to know if the normal Beam virtual machine is too big for it. It depends. So I use the Unix platform, the Unix platform output from AtomVM. It's a good enough one, but just as a reminder, there's missing features. When I try to use, for example, the OTP library in Gleam, I had to do a hard fork from the original one for the INSI framework specifically, because some of the tools were not working. But what I believe is more like we may want to reach the AtomVM team and share resources. And probably with a very good conversation, we can figure something out that almost all the features that the Gleam needs make sense. But just as a reminder, AtomVM has a specific goal to be small and to have that specific niche. And that's why I'm not sure if wasn't it's going to be a good fit for the INSI framework, because in general the INSI framework is thinking more on hardware peripherals integration more than anything else, but at least can be like an idea on how to use the VM, like a starting point for something else if someone is going to do something fancy in the web space. Yeah.
Got it. Thank you so much. Any more questions from the audience? Okay. If not, let's give a round of applause to Ray. And thank you so much for this presentation.
Thank you, everyone.